A small crater hosts a layered sedimentary mound that poses fundamental questions. Are these layers sedimentary rock or ice-related materials? Do the layers display quasi-periodic bedding patterns? The latitude creates ambiguity. This could be an outlier of Becquerel crater, or it might be a younger outlier of mid-latitude glaciation. High-resolution imaging searches for sublimation features. These features would reveal whether ice plays a role. The goal is determining if this represents a sedimentary rock outlier. Understanding the composition unlocks the formation history. Rock and ice leave different signatures in texture and layering. A small crater under 1 kilometer across sits on a ridge northeast of Hellas Planitia. An exit breach cuts through its western rim. The configuration raises a provocative question. Did water once fill this crater to the brim? Overtopping could have triggered a catastrophic flood. This crater might exemplify the same process that caused large crater lakes and massive floods. Aram chaos experienced such flooding on a far grander scale. If confirmed, this small crater provides a manageable analog. Scientists could study flood mechanics here and extrapolate to larger systems. The breach geometry holds clues to water depth and flow velocity. A sharp-rimmed crater 11 kilometers in diameter displays an unusual exit breach. The breach appears both sinuous and poorly developed. This characteristic intrigues researchers for a specific reason. Most low-latitude fresh craters completely lack exit breaches. Why does this one possess such a feature? Stereo pair imaging can measure outlet breach depths and slopes precisely. These measurements reveal formation mechanics. Did water carve the breach gradually, or did catastrophic drainage create it rapidly? The sinuous path suggests multiple episodes or complex flow dynamics. Understanding this crater helps explain when and how breaches form. Material in Vastitas Borealis appears to deflect around a small hill. This pattern suggests the formation arrived as a mudflow. Detailed flow morphometry can constrain the flow morphology and behavior. Vastitas Borealis ranks as the largest lowland region on Mars. It spans the northern latitudes, encircling the polar region completely. The relationship between flowing material and topographic obstacles reveals rheological properties. Did the material flow like liquid mud? Or did it advance as a viscous slurry? The deflection pattern around the hill preserves information about flow thickness and velocity during emplacement. Frosted gullies cascade down an irregularly shaped pit approximately 15 kilometers wide in Sisyphe Planum. The pit occupies an impact crater about 35 kilometers across north of southern polar layered deposits. Carbon dioxide frost blankets the region, revealing subtle textures. Layered sediment in pit walls likely once filled much of the crater. Dark, low albedo spots along gullies mark defrosting areas where carbon dioxide sublimates during spring. Polygonal patterns indicate near-surface ground ice. Ice-rich landslides and sinuous ridges run along the pit wall base, driven by unstable layered sediment. Bright rocks in Noctis labyrinthus contain minerals that hold water within their crystal structures. The CRISM instrument detected these water-bearing minerals from orbit. Combining spectral data with high-resolution images allows scientists to understand how water altered these rocks. Many depressions in Noctis labyrinthus host water-bearing minerals. Water remained available during the late Hesperian to Amazonian epochs. Climate models indicate Mars was already dry and cold during this time. Yet, water somehow persisted here. The minerals preserve chemical evidence of water-rock interactions that shape the landscape. Context camera data drives an intriguing hypothesis about this crater floor. Could a paleolake once have filled this basin? The landform rising from the floor stands as an outlier of the central peak. Did it once function as an island in that ancient lake? The geometry supports this interpretation. Islands form when water levels rise high enough to isolate elevated terrain. If confirmed, this would mark the ancient shoreline position. Sediments deposited at different water levels could ring the landform. Understanding whether lakes existed here reveals climate conditions. Lakes require sustained water input and limited evaporation. A light-toned deposit occupies chaotic terrain at the base of Valles Marineris. The deposit displays a rough surface contrasting with surrounding smooth areas. Some portions appear eroded by fluid flowing north and south. Alternatively, wind may have sculpted the patterns. This deposit may relate to interior layered deposits found throughout Valles Marineris. Those deposits likely formed in ancient lakes. The rough texture could indicate differential erosion of layered materials. Harder layers resist erosion, while softer layers wear away faster. Arsenos chaos marks where chaotic terrain meets canyon systems. An intriguing textured surface sprawls south of Hellas Planitia. Could ice loss have created this texture? The hypothesis requires testing through detailed observation. The search includes looking for boulders and polygonal shapes. Polygons often indicate ground ice beneath the surface. When ice sublimates or melts, overlying material can collapse, creating patterns. The texture might record past ice table depths. Different ice concentrations produce different surface expressions. Understanding whether ice loss drove formation helps reconstruct climate history. Ground ice distribution varies with latitude and local conditions across Mars. A small impact crater under 2 kilometers across sits south of Arsia Mons in Daedalus Planum. Lava flows have enclosed the crater on all sides. The lava never overtopped the rim. The crater stands as an island in a frozen lava sea. Context camera images reveal small-scale geological characteristics. HiRISE examines these features in better detail. The relationship between crater and flows constrains timing. The crater formed before lava arrived. Understanding flow thickness explains why lava stopped before the rim. This crater provides a depth gauge for surrounding lava deposits across the plain. The southern branch of this channel stands high above its surroundings. When the flow waned, the northern channel cut deeper, leaving the southern branch isolated. This configuration preserves evidence of changing water levels. The high-standing branch marks the earlier flow regime. As discharge decreased, water concentrated in the northern channel. Erosion deepened that channel while abandoning the southern branch. This location offers an ideal opportunity to search for fluvial deposits. Sediments carried by ancient flow likely settled here. Finding deposits would confirm water transport and deposition in Elever Vallis. Prominently stratified rock cuts through a mountain of material in the middle of Hebes Chasma. Knobby material showing several lineations occupies the center of the scene. These may be landslide remnants that expose the tall, steep slopes visible here. Midway up the slope, alternating lighter and darker bands run east to west across ridges and troughs. Just below this banded section, dark material erodes off the slope. It moves downhill and collects in fans at the cliff base. Layered rock exposures like these reveal geologic processes operating over time. The landslide and fan deposits show how erosion continues today. Dark-toned dunes populate several craters within the rugged terrain of Terra Cimmeria. Sand dunes on Mars frequently occupy craters. Do they form from materials within the craters? Or do craters simply trap traveling dunes? The dune avalanche slopes, called slip faces, point southward. This direction indicates dunes have been transported in and out of craters on their path south. Wind drives the migration continuously. Smaller sand patches appear anchored in depressions where wind cannot effectively initiate motion. These traps hold sand indefinitely. The pattern reveals craters as both traps and temporary rest stops for migrating dune fields. Monitoring of the Happy Face crater in the South Polar region spans almost a decade. 2 images taken in 2011 and 2020, at roughly the same season, show color variations. Bright frost covers darker red ground in varying amounts. Blobby features in the polar cap form as the sun sublimates carbon dioxide into round patterns. 9 years of thermal erosion enlarged the mouth of the face. The nose consisted of 2 circular depressions in 2011. By 2020, those depressions grew larger and merged together. Sublimation continues, reshaping the face year after year. The changes provide insight into polar cap erosion rates. Stratigraphy appears exposed in an approximately 1 kilometer wide crater at this Meridiani Planum location. The expression of layers can be traced around the ridge on both sides of the exposure. Layer continuity suggests intact deposition. This feature may prove useful for understanding crater mound deposits. Some mounds involve sediment deposition in ancient lakes. Others invoke wind deposition over millions of years. The layering pattern could distinguish between hypotheses. Measuring layer thickness and composition reveals the depositional environment. Understanding this mound unlocks formation mechanisms debated by planetary scientists. A valley fills with linear ridges called transverse aeolian ridges, or TAR. They take various forms across Mars. Here they sit at right angles to the valley direction. The topography funnels wind along the trough, shaping ridge orientation. Some TAR display secondary structures, likely small ripples. Sand dunes commonly host small ripples with different orientations. Winds redirected by larger dunes shape these features. The ripples record wind patterns at different scales. Understanding TAR formation helps reconstruct wind regimes. These ridges preserve information about atmospheric circulation on Mars. Channel and fan deposits within Peridea crater warrant further analysis at high resolution. Context camera pictures show these features but lack detail. The layering and shape of the fan suggests possible stepped fan formation. Stepped fans form when water discharge fluctuates over time. Each step represents a different flow episode. Peridea crater spans about 100 kilometers in diameter in the Syrtis region. The crater may have hosted a lake that received sediment from incoming channels. As water levels changed, the fan prograded outward in steps. Understanding this deposit reveals the hydrological history of Peridea. Jarosite, a potassium and iron hydrous sulfate, appears throughout Eos Chasma in Valles Marineris. The Opportunity rover first identified this mineral on Mars. Jarosite proves useful in retaining textural and chemical evidence of past conditions. It forms in acidic, watery environments. Finding jarosite indicates acidic waters once flowed or pooled here. The mineral ranks as common across the red planet, appearing in many locations. Jarosite-bearing strata in Eos Chasma may record episodes of acidic water chemistry. Understanding when and how these minerals formed reconstructs ancient environmental conditions in Valles Marineris. Exposed ejecta west of Hargreaves crater shows up in the MEAS and context camera images. The goal focuses on studying rock breccia fragments and clarifying boundaries for mapping. Ejecta represents material thrown from the crater during impact. Analyzing fragment sizes reveals impact energy. Hargreaves sits between the two largest valleys of Nili Fosse in the northern hemisphere. The location places ejecta in an interesting context. Did the impact excavate through multiple rock layers? Fragment composition could answer this question. Mapping ejecta boundaries constrains the area affected by the impact event. Exquisite layers cut across steep slopes in Burroughs crater. These layers may be very thin, requiring high-resolution examination. Topographic information would prove valuable for analyzing the paleoclimate record. Each layer represents conditions during deposition. Burroughs spans about 104 kilometers, honoring American author Edgar Rice Burroughs. This crater sits within the 180-kilometer Baldet crater in the northern hemisphere. The location ranks as a good candidate for recurring slope lineae. Few candidates exist in this region on north, south, and west-facing slopes. The layers may preserve climate variations. Exquisite layers blanket deposits in Burroughs crater. These layers may be very thin, requiring high-resolution examination. Topographic information would prove valuable for analyzing the paleoclimate record. Burroughs measures about 104 kilometers in diameter, honoring American author Edgar Rice Burroughs. Each layer preserves a snapshot of past environmental conditions. Variations in thickness and composition record climate changes. Analyzing the sequence reconstructs climate history spanning millions of years. Understanding what drove these changes illuminates Mars' climate dynamics over geological timescales.